later.
No, because you're going to accidentally add that one.
Hi,
Kayla.
Sorry, you're sick. I don't know if you're sick. If you're sick, I hope you feel better.
No, they're both sicky. Okay, so we're going to intro today.
Maybe you should wash your hands.
Significance testing.
You got Roger Williams tour.
USM?
USM.
Yeah, I toured.
Then I saw you there.
I know, I didn't see you.
Hey, I'm going Florida Southern. Whoa.
Where the heck is my note sheet?
Why is my lunchbox?
Can I go to Simmons?
It's all women.
Maybe I want
You're
to
going to do it all
Women
women's
is
school.
Why would you ever do
No, they
that?
have classes with like all the other colleges with all the guys.
You don't want to become an activist.
They have one.
That's the
All right, here goes, people.
That's an
All right, ready? Shh, focus. That's up to you. All right, so today's like introduction day to what it means to talk about a significance test, right? So we're going to talk in general today, and then next class we'll talk about proportions, and then the next class will be means, because that's, as I've said, how things progress. Okay, so a little bit of notation to start with. So when we are looking at a significance test, we are looking to weigh evidence against what is called the null hypothesis. Now, you may have talked a little bit about hypothesis testing in like a science class, maybe. Like I feel like when you guys do those like big science projects at the end of the year, there's some hypothesis test stuff.
Does that say null?
H-O.
The null hypothesis, which is H sub 0. So that is our notation moving forward for the null hypothesis. So we're trying to find evidence in favor of what's called the alternative hypothesis, which, again, moving forward, is going to be uppercase H sub A. All right, so that's our notation for the null hypothesis and the alternative hypothesis. Again, today we're going to talk kind of in general. We're not going to do any actual calculations. We're going to talk about what the write-ups look like, how we draw conclusions, and then next class we'll talk about where the numbers come from that we use to draw the conclusions, because they come from somewhere. Here's some things you need to know. You need to know that it's always about parameters. So our parameters are mu and p. So you're never going to write a hypothesis concerning x bar or p hat. You can only use mu and p to write your hypothesis statements. So you can have hypothesis statements that are one-sided. So one-sided statements are going to have greater than or less than symbols in them. Or we can have something called two-sided. And to be two-sided, you will have a does not equals. Now, this all looks pretty meaningless right now, so stick with me while we get through some of the like notation stuff, and we'll talk. We'll get an example. All right, so here's the deal. Your hypothesis statements are going to look sort of like one of two ways. I'm going to make a little line here and just give you like a couple of examples of what hypothesis statements look like. So you could have a hypothesis statement about a mean. So you could have, say, a null hypothesis, and we use like a colon there, so it's like H sub 0 and then a colon. And I might have some like hypothesized value. So I'm going to make up something. I'm going to go to one of my go-to things here,
Test.
which is test scores. So, next year, when you're taking that class, you'll get a test score. And suppose the mean was something like 75, usually in like a freshman math class. The mean is 75. And we have reason to believe that that mean has changed over the years. So a professor gives the same tests year after year in his freshman math class. And every year his mean is right about 75 on this one particular test. But he's noticing recently that he feels like the students are coming in a little bit stronger. And so he thinks that the mean is going to be greater than 75. All right, so you're with me? So the mean has always been 75, and now he's like, there's some stuff out there that makes me think it might be higher than 75 now. So the null hypothesis is that the mean is 75. So, null
is that a 10?
hypothesis is that the mean, that's our mu for mean,
Oh,
is 75.
I thought. See, I was thinking it was N-O, like no hypothesis.
No. H sub A. So then we have an alternative hypothesis. So he thinks the mean is getting bigger than 75. So his alternative hypothesis will be that mu is greater than 75. Now, when you write a null and alternative hypothesis, again, you can only use mu or p. This was a mu example. I'll give a p example in a second. Your null hypothesis is always that it equals something. Okay, so null is always it equals something. The alternative can be greater than, less than, or not equal to that same number. I can't have a 75 in my null hypothesis and then a 78 in my alternative hypothesis. Okay, those two numbers have to be the same. So in a proportion, I might see something like this. I might be like, hey, the null hypothesis is that in New Hampshire, the proportion of people who own dogs is 78%. So my null hypothesis is that p equals 0.78. But I think that that's changed for some reason. And I don't know if it's gone up or gone down, but I think it's different than it used to be. So my alternative hypothesis would look like this. P does not equal 0.78. So again, it has to be the same number, right? It has to be 0.78, it can't change. Your null hypothesis is always that it equals something, and your alternative can be greater than, less than, or does not equal. Never use x bar or p hat when you're writing a hypothesis statement. You can only use mu or p, parameters only, not statistics. Okay, so keeping that in mind, I'm going to read this little example here, and I would like to see if you can write a null and alternative hypothesis.
Wait, what?
So reading that example, see if you can write a null and alternative
What is
hypothesis.
irrigation?
Take from the water of the plants. Irrigation. So I'm looking for a null and an alternative hypothesis.
Can I? I never got to fill
Yeah.
it out.
Okay, so this is about means. I see the word mean there. So it has to have a mu. So my alternative null hypothesis is that mu equals, it's always equals. Null hypothesis is always equals. And let's see, the mean weight was 31. And they want to know if this has changed. They don't say up or down, they just say changed. So my alternative is, do we think that it no longer equals 31? Now,
What did we do? Up at the top, we did half. Sorry, just greater than or equal to.
right here.
Yeah.
So again, your alternative is going to be one of three things. You have to read the problem to determine which thing. It could be a greater than, it could be a less than, could be a does not equals. In this case, it just said has it changed. We'll do another one. But I want to point something out. There's more room here because you got to write something else here. We need to define the parameter. So I'm going to write here where mu equals the true mean weight of all pineapples at this company. So we're defining our variables.
Can I guess and say that it'll be more than 31?
You may not guess. Some data would need to be collected and a test run. And like I said, we're not going to get to any of the calculations today. We just won't be able to get to that today, but we will next class get to calculations. Right now we're like practicing what the notation looks like, and then we'll talk about how you draw conclusions if you have the data. Okay, so here's another one. We have Joe, and his free throw percentage last season was .80. and a local reporter thinks that that's gone down. So we're going to write a null and an alternative hypothesis for this situation. Here goes. Null hypothesis. Okay, this one's about proportions, because it was this free throw percentage. So the null hypothesis is that p equals 0.80. So our alternative is about the fact that the reporter thinks that's gone down. So alternative hypothesis is that p is less than 0.80, gone down. And again, we're going to define our variable where p is the true proportion of free throws that he makes. All right, so again, you're going to read the scenario, you decide whether you're looking at a mean or a proportion. We've talked a lot about that. And then this is what our null and alternative hypothesis statements are going to look like with a variable defined. All right, so then you'd have to have some data get collected. So like, here's the deal. You have to construct your hypothesis statements prior to data collection. So you can't like collect a bunch of data and say, hey, look, my pineapples are heavier than they used to be, and then run a significance test. Right? You have to say to yourself, I have something that I think has changed for some reason, so I'm going to test it. I'm going to write my statement to test, then some data will get collected, and calculations will happen. We're not going to do that today. Once the calculations happen, you get this thing called a p-value. So we will calculate a p-value. So I want to talk about what a p-value is. It's a very specific definition. Okay, so p-value is the probability assuming that the null hypothesis is true. So it's all based on making this assumption that the null hypothesis is true, okay? So this is the probability, assuming that the null hypothesis is true, that a statistic take a value as extreme or more extreme than was observed. So suppose in the pineapple problem, for example, like last year the mean weight of the pineapples was 31 ounces. I put this new irrigation system in, I want to know, hey, has it changed the weight of my pineapples? So I go out and I get a random sample of some pineapples and I do some calculations and I get a p-value. So small p-values are what you strive for. Small p-values give you evidence against the null hypothesis and help you prove your alternative hypothesis, right? So if I got a p-value, say 0.01 related to the pineapple problem, I'd be like, hey, there was only a 1% chance of this happening. That's really unlikely. Think about the free response question we just did, and we said, like, when something's really unlikely, that's like evidence against what was previously thought to be true. Okay, so small p-values are evidence against the null hypothesis. And that's kind of our goal. We're trying to disprove the null hypothesis. And that's because it's unlikely to occur by chance. Now, again, if you think of the free response that we just did, and we had that problem where it was like a 0.01 chance that it was just women selected into that group of 3, like Maya said, but it could happen. And it's like, yeah, it could happen, it's just that it's really unlikely. We can never in stats say something is 100% definitive, right? So we try to talk about how unlikely something is. Okay, so suppose on this free throw problem, some data was collected. Again, we'll talk about all of the background stuff next class, but suppose some data was collected and we got this p-hat value, and I got a p-value of 0.0075. This gets a little confusing because there's p-hat, and there's p, and there's p-value. It's your three different things, right? So remember that P is your population parameter for the proportion. P hat, it's impossible to find the little like hat mark on Google Docs. So I wrote hat, but it's that P hat that we've talked about before. That's your sample statistic. And then there's this P value. Okay, there are three different things. So the P value is 0.0075. That is a teeny tiny P value. That is really good evidence against the null hypothesis. We feel pretty good saying, yeah, I don't think that his free throw is 0.80 anymore. I'm pretty sure that it's gone down, right? So let's write down exactly what this P value of 0.0075 means. It means there is only a 0.75% chance of obtaining the P hat value if he truly still has a 0.80 free throw probability. So here's what we're saying. Have this guy who claims to be a 0.80 free throw player. We collect a sample and we're like, hey, you only made 64% of the shots in your sample, not the 80% that you claimed. Maybe I just happened to pick a sample that, like made him kind of look bad. There is a 0.75% chance that I just got a sample that happened to make him look bad and he still really is an 80% free throw shot, but that's really unlikely.
So, I'm confused about the P hat part.
Mm-hmm. So P hat, remember what P hat is. P hat is from your sample, right? So here's what happens. I go out and I take a sample, and in the sample, he made his shots 64% of the time. So I'm comparing this sample that I took to the claim that he made previously about being an 80% shot. And remember, this is all about variation, right? Like there's variation in your sampling. If somebody says they're an 80% shot, that doesn't mean that like every sample you take, exactly 80% of their shots will be made. Some will be higher, some will be lower. The question is, how unlikely is it that he only made 64, right? And it's pretty unlikely that he only made 64, and that's evidence against the claim that he's an 80% shot. Once we start doing some examples, this will become clearer. It's a little unclear at first, I know. All right, so let us continue on. Okay, this is important. There's only two options here. Once you get a p-value and you look at it, there's only two things that you can say for your conclusion in context of the problem. Okay, the first one is that we reject the null hypothesis because there is evidence against it. Okay, so we can reject the null hypothesis because we have evidence against it, and that means we're now in favor of the alternative hypothesis. Okay, or the second thing, and this sounds weird the first few times you hear it, but you're just going to get used to hearing it and it won't sound weird anymore. You fail to reject the null hypothesis.
So you basically are proving it right?
You can never say that.
Proving it maybe right?
You can say that you don't have evidence against it, but you can never say, hey, I just proved the null hypothesis to be true, okay? So you can fail to reject the null hypothesis because there is not convincing evidence against it. Okay, so you can either reject the null hypothesis in favor of the alternative, we'll practice this right up, or you can fail to reject the null hypothesis because you don't have enough evidence against it. But you can't say, I accept the null hypothesis. Don't ever do that. Either reject the null or fail to reject the null. And we want to get context in, as usual. Okay, let's talk about an alpha level. So we're going to use the Greek letter alpha, it looks like this, to represent our alpha level. Yep. That's what it looks like.
It's like a
Fish.
just
Or look right here.
sideways.
It's a fish.
Kind of looks like a curly A or a fish. Depending on the font, it can look different.
It's a sideways cancer
Symbol?
Yep.
The ribbon.
Okay, let's talk about the alpha level. The alpha level has to be set in advance. So when you are setting up a hypothesis test within the body of the problem, it will tell you the alpha level. If it doesn't tell you the alpha level, we default to an alpha level of 0.05. We'll talk more about that next class. The alpha level is what you're going to compare the p-value to. Okay, so a typical alpha level is 0.05, but it could be 0.10, it could be 0.01. The stronger evidence you want against your claim, you would want to make your alpha level smaller. So what we're going to do is we're going to say if the p-value is less than the predetermined alpha level, we reject the null hypothesis. So this is how we're going to make our decision. And I alluded to this a little bit kind of leading in, like we've talked about how small probabilities are evidenced against something, but now we can be really specific because now we'll have a cutoff. It's like an alpha level will be set at 0.05, and we're going to compare the p-value that we calculate to that 0.05, and we're going to do one of two things. We're going to reject the null hypothesis in favor of the alternative, or we're going to fail to reject the null hypothesis because there's not enough evidence. So this is nice because there's like this definitive like cutoff mark. It's not this, I'm not sure, is it large enough, is it small enough, like what's happening? Okay, so let us discuss. Here's the situation. We've got a battery company, and they have this new product that they've developed, and they think that they have increased their battery life from what was previously known to be a mean of 30 hours. So their old batteries lasted a mean of 30 hours. They're like, hey, we've improved our batteries, and we now think that the battery life is longer. So they're going to have to set up some sort of sampling situation and collect some data. All right, so let's write a null and alternative hypothesis.
No, I'm so sorry.
Okay, the null hypothesis is about the previously known 30 hours. So our null hypothesis is that mu equals 30, and we now think that it's greater. We think we've improved the product. And we're going to define mu over here, which is the true mean battery life in hours. So again, somebody has to go out and take a sample and do some calculations. Wednesday and Friday we'll talk about that part. Somebody goes out, they take a sample, they do some calculations. And here's what they say to you. They say, hey, I got a p-value of 0.0729. And we are going to draw a conclusion now based on this p-value that somebody calculated for us.
How do we know?
Again,
No,
that's
we're doing that
coming.
next class.
You can't do everything at once right now.
But
really.
where did you get it?
So you have to imagine that somebody went out and took a sample of a whole bunch of these batteries and tested them to see how long they lasted. And then they did a whole bunch of calculations that we'll discuss later, and this p-value popped out.
So will we learn how to do
Yes.
this?
She said that.
I was yawning.
Listening
You're
to
wrong.
Do your ears cancel out when you
You're wrong. Yeah,
Actually, I think they do.
they do.
All right. Anyway.
Yeah.
All right, so somebody did the calculations and we have the p-value. Our focus right now is like, what do we do with the p-value? Not where did the p-value come from. What do we do with the p-value? All right, if your p-value is below the designated alpha level, you reject the null hypothesis in favor of the alternative. So I'm looking at my p-value, and if the alpha level was 0.10, well, the p-value is less than that. So I would say because the p-value of 0.0729 is below the alpha level of 0.10, This is the situation where we reject the null hypothesis. We reject the null hypothesis, and then we're going to write some context in here. There is evidence that the mean battery life is greater than, because that was our claim at the beginning, 30 hours. You can't say any more than that. You can just say what your alternative was. And our alternative was just that mu is greater than 30. All I can say is I have enough evidence at an alpha level of 0.10 to reject the null hypothesis and say that I think my alternative is true. All right. The p-value was below the alpha level. The alpha level has to be preset. You can't set it after you've collected the data to make it like say what you wanted it to say.
How do you choose?
So you'll be told in the
Oh,
problem.
okay.
You'll be told.
Okay.
Okay, if the alpha level was 0.05, I would have to draw a different conclusion,
We're gonna have to fail to reject.
right? So I would say because the p-value of 0.0729 is greater than the alpha level, we fail to reject the null hypothesis. And we will actually say there is not convincing evidence that battery life is greater than 30 hours. Now, again, it's dependent upon the comparison of the p-value to the alpha level. And you will be told an alpha level within the problem. If you're not, you default to 0.05, but you have to state it prior to calculating the p-value. You can't calculate the p-value and then say, ooh, I'm going to set my alpha level at 0.10 so that I can reject the null hypothesis. It has to be set in advance. So what you'll see is things that are more of a high stakes things like medication testing, their alpha levels are going to be low because they want to like really ensure that the data is saying what they want, that they're safely saying what they want it to say. All right, we're going to do some practice of some of these little things. So on your paper you can see it says do page 551, those problems. So we're going to stop here for now. No, we're doing it now. Hopefully going over it. Okay, so we'll pause here.